Hello. So we're going to talk about section 3.3, relative motion. So to start this section out, we should know a couple things. One, we're going to be using vectors again. Remember, we use vectors. We are going to show a letter with an arrow above it showing the direction of which it goes. And so that's what you see highlighted here. Now, we talked about resultant vectors already, and remind yourself that a resultant vector is a single vector that is the sum of two or more other vectors. So it's showing that they're adding them together in the same direction. Now, when we talk about our relative motion, we want to make sure a couple things. We will always have what we call a reference frame. It's also referred to as a frame of reference. I'm going to call it a reference frame. That's what your book also calls it. So that is why I'm using that terminology the way I am. So a reference frame is just looking at that information that we see at a fixed point so we can measure the direction relative to that. So a mile marker is a great reference frame. And so we see that a frame of reference or a reference frame is something that we can use to show how far away we are from something because we know where it's at. Like from Warner to Aberdeen is a reference frame, or the Warner School, go north from the Warner School, or take a right after you leave the parking lot. Those are reference frames so that we understand that. We're also going to talk about inertial frames. An inertial frame is dealing with inertia. And inertial frames are really quite interesting when you think about it, because it's the perspective in which we see, or a reference frame of which we see that the observer are not subject to any accelerating forces, such as you in a car. Sometimes when you're in a car, you will have an understanding that you're moving, but you really don't feel it. And so let's look at our two cars here. So when we start looking at this question, what is the velocity of car B relative to the velocity of car A? So we want to kind of look at this a little bit. So we know car A is headed east. Again, we're on the x-axis. We're on the x-axis for both of them. This car B is headed west. So what do we already know about this? Well, west is negative, east is positive. We don't have any y-axis, but I want to talk about that really quick. So a y, we would go up, would be north, and down would be south. North would be positive, south would be negative. So I just want us to kind of have that frame of understanding when we start talking about some of these directions on both the x and y axis. So remember that east is positive, west is negative on the x, and on the y we have a positive north with a negative south. So what is the velocity of car B relative to that of car A? So we're going to use the equation of above. We're going to solve for velocity, so we're going to make it a vector. It tells us what we need car B compared to car A. And so we're going to put a B first for car B to car A. And so in order to do this, we need to make sure that we're looking at the velocity of B vector minus the velocity of A vector, because we're comparing them. Remember, I am in car B and don't feel any motion. That's why sometimes when you look down at your speedometer, you're going a lot faster than what you think you're going, because you're not feeling that inertia or that motion that's occurring to you. So if we put this into the equation here, we can see that car B has a velocity headed west, so it's going to be a negative 60 miles per hour. And we're going to subtract that from car B that's headed east. And that's a positive 30 miles per hour. And so if you're in car B, you're going to feel like car A is moving at a negative 90 miles per hour. Again, the person in car A sees car B moving at a different rate, but we're looking at the perspective of just car B. Car A is coming at them and they feel motionless, and car B is not feeling the same inertia as car A, and they feel like car A is moving at a negative 90 miles per hour. But what if we look at it from a different perspective? Again, we're looking at perspective when we deal with these vectors. What if we deal with the vector showing the relative velocity of car A compared to B? Well, we're going to use the same equation from above. Our vector B would go second this time instead of first, because it's not the perspective we're first dealing with. We're not sitting in that car anymore. We're sitting in the other car. So we're still subtracting. So again, from car A, that's a positive 30 miles per hour minus car B is headed in a negative direction of 60 miles per hour. And so car A perspective is a little different because two negatives make a positive. This would be a positive 90 miles per hour. And I'm sure we've all been in those cars where somebody's whizzing by and the other car is moving much faster, or twice the speed as you. And so they look like they're traveling a lot faster than you are when they're going in the opposite direction. And cars that are moving half of your speed feel like they're going a lot slower. And so that's why we see the slower moving car having the perspective of car B moving 90 miles an hour faster than they are, while car B is having the perspective of car A moving at a negative or a much slower rate than they are. And so when it comes down to these two questions below, which car has the positive motion? Well, or the positive motion, we know that car A has a positive eastward motion, and which car has a negative motion? We know that car B has a negative eastward motion, as we showed it you above. But what happens if the two cars aren't moving on the same coordinate plane? What if they're not moving on just the y-axis? What if they're moving on both the x and the y-axis? Well, that's a little bit different. Again, remember, x, we have positive east, negative west. Y is going to be positive north, negative south. So if we look at this right here, and we see these beautiful cars moving in this direction here, we know that this is a beautiful 90-degree angle, and these two angles right here are going to be 45. Just like in section 3.2, it's really important that we know the magnitude and the velocity of these. Because car B is moving north, we know this is positive. And because car B is moving east, we know it is also in a positive coordinate plane. However, we're going to look at the resultant vector from this car, which is a little bit different. So what is the velocity? Oops, I apologize. So right here, what is the velocity? Of car A relative to that of car B. And so we want to use that same velocity vector at car A. That velocity A to B, these are supposed to be subscripts, I apologize for my cursor, is now equal to our vector A minus our vector B. However, in this case, we know that there is an x and y coordinate to this, so it's a little bit different than what we did on the first, where they're both on the x-axis. we now have an x and y, and so we need to account for both our x and our y coordinate. So car A has an x component because it's moving eastward of 30, while the y component for this is 0. It's still on that axis as far as we're concerned. And so then car B has an x component of 0. And we're going to subtract that because remember we have this subtraction thing in here. And so we're going to minus that from our positive 30. So we just have a negative. So our x and y value now, because we are on both the x and y axis, is going to be a positive 30 with a negative 30. So if our x is positive, then that tells us we are moving east. And if our y is negative, it tells us we're moving south. And so our direction is southeast. So again, when we start looking at some of this stuff, we still don't have both a magnitude and a direction for this. We now know that we're moving southeast, which is great. So the problem is we just said that we have a 45, 45, 90 triangle, but we're headed southeast, which puts us in the fourth quadrant instead of the first quadrant. So now our angle isn't going to be that beautiful. Same, our angle, because we're in the fourth quadrant, is going to be 315. So it's completely flipped. And so remember that when we flip these quadrant planes, we're not in the first quadrant. We started in the first quadrant, but because we're moving southeast of south, we are now in that fourth. But we don't have a magnitude yet. So again, Pythagorean theorem. So C is going to be equal to the square root of, well, we have 30. Squared plus 30 squared, which is giving us 42.4. And again, we have that 315 degrees because we're traveling east of south on a 45, 45, 90 triangle going the opposite direction. What if we reverse that perspective though? So again, this is the perspective of person A looking at car B. But what if it's the opposite? So we still have our velocity vector, but this time car B is going to be first and car A. We are going to have them equal to, again, the equations on the front page. Our velocity B, correction, plus our vector minus our vector A. And so again, we're still using those same. So we have a 0 plus our 30 and our negative 30 with 0, giving us that coordinates for our 30 for the x and negative 30 for the y. Again, we're just now in a reverse direction for this than we were before. And so we still have the same magnitude because it's still 30 and 30. So that is our 22.4 units. 42.4 units. That magnitude has not changed for that. I wrote this incorrectly on the answer part right here. But we want to make sure that we have this 30 and minus 30. We have a reversal in direction because of how we're seeing this. And so we do have our coordinate plane being at 315 because now we are going east. And I wrote this backwards. I so apologize for this. because we have our x coordinate being a negative 30 because this is actually going negative, and a positive 30 here. So we are now going west and north. So we're at 315 for this. With this, we want to make sure that we are looking at those quadrant planes and their importance as they go through. So here is an example of another one. The world's fastest canal is in Canada with speeds that reach over 30 kilometers per hour. Suppose you are crossing a motorboat perpendicular to the bank with a speed of 18 kilometers per hour relative to the bank. Find the velocity of our motorboat. So we know a couple things. We know the perspective of the water, so we know the velocity of our water to the bank because we're watching this from the bank. We know that that is 30 kilometers per hour. And so this is a perspective. I'm going to draw this so we can see this. And so we're drawing this in that 30 kilometers per hour here. And this is our velocity of the water to the bank. And we know that the motorboat is moving perpendicular. So we get the velocity of our, I'm going to put MB for motorboat. Again, these subscripts can be whatever you remember them to be so that we kind of find them. So we got the motorboat's velocity, and that's moving perpendicular. So we know it's moving in this direction. And that is moving at a total of 18 miles per hour. I apologize. My screen is not allowing me to always put information on. So this is going at 18 kilometers per hour. And so we need to find this vector right here. We need to find, as the motorboat is crossing, the speed of that motorboat as it's going here, because it's going to be moving in this direction because of that resultant vector. It's not going to go straight across. It's going to be moving in this different direction. So we need to use the equation. We're going to put MW, the motorboat in the water, is going to be used to MB plus R vector W, boat, water near the bank. And so with this, we already know that we have 18 and 30, so we can actually put this into the Pythagorean theorem right away. And we know that this is going to be our 18 squared plus our 30 squared to find our magnitude of the motorboat in the water. And so we get this at 35 kilometers per hour. And so we already kind of know that equation because we're already solving for this and can see that. So if we need to now find we have one more that we have to find because we only have a magnitude now. We need a direction. So we know that our inverse tangent, because we don't have our tangent, our inverse tangent is going to be our 30 divided by our 18. And when we put this in, we are going to get 59 degrees. And that's away from the current, the oncoming current. So we're moving in a separate direction than the oncoming current because we're coming at that angle and it's pushing us across the water. And so the water is moving in this direction. We're moving in this direction. And the boat looks like it's moving like this across the water because of that.